This video describes the function f of z is equal to z squared and its inverse. Now you would probably think that a function so simple as z squared doesn't really require a whole video, but it has a whole bunch of interesting structure that's worth exploring. And it's best explored using polar coordinates. So let's write z equals r e to the I theta where r is equal to the magnitude of z and theta is equal to the argument of z. Now if I say w is f of z, so z squared, that's r squared e to the 2I theta. Right away you should notice that f of any kind of unit complex number is still a unit complex number. So this function preserves the unit circle. However, it wraps around twice. This is called an index to a degree 2 map. Because it goes around twice. So, graphically, here's the real part of z and the imaginary part of z. Here's the imaginary part of w and the real part of w. If I take the unit circle, go around once, well, in fact, what happens when we map it by w equals z squared is that the unit circle still is the unit circle, but we go around a second time before coming back to where we started. I've separated the strands of the map a little bit so you can see that they're both there, but they really lie on top of each other. And in fact, every point except for the origin has this happen. So in fact, the entire upper half plane gets mapped to the entire plane here. So the upper half plane maps to the entire complex plane. Every point in the complex plane therefore ends up showing up twice in the image. Or put another way, every point in the w plane except w equals 0 has two pre-images in the z plane. Why is that? Well, the reason for that is because of this. This is the cause of that phenomenon. The cause of that phenomenon is the fact that my angles get wrapped around twice. Now, every point that is within the unit circle, in here, on the upper half plane, where does that end up going? Well, each one of those has a magnitude of less than 1. When I squared it, still has a magnitude of less than 1. So it ends up in here. Everyone outside stays outside. Okay. Now, the point is that I didn't have to pick the upper half plane. I could have picked any half plane, and this would have happened. And so this double circle business shows up everywhere. It's a little hard to see, but the fact that the origin is special and everything's gotten twisted around the origin is kind of doesn't really fit in 2 dimensions nicely. It fits in 3 dimensions reasonably well, And so let me show you a picture of that. This is how it looks if I were to stretch out those two layers. I've artificially stretched them out vertically. And so what you can see, if I look down from the top, the positive real axis is right here where the colors lie together. The origin is right there. And everyone around here has gotten wrapped around twice. Now if I look in from the other end, look down from here, you can see that these two sheets come together. It looks like they intersect, but in fact they don't. They're not. They're entirely two separate things, as I've wrapped around twice. The origin is really got a rather striking structure to it. The origin is called a ramification point in this case, and I have these two pieces coming together. These two pieces coming together suggest that if I try to do the inverse, I'll get a branch cut. And indeed that happens. So what does this mean? This means that for the inverse, f inverse of w equals z, such that that makes sense, that's a multiple valued function, i.e. not really a function, but kind of like a function, is multi-valued, and therefore will have a branch cut somewhere. Again, branch cuts are not entirely real, just like with e to the z in logarithms, because if I look at this surface over here, that surface is perfectly smooth. There's no real problems why you would say that there's a discontinuity. There's no discontinuity. But the branch cut is where I switch from one sheet to the other. In particular, if I try to compute what ends up happening when I've got two pre-images, something like this is what I see. I'll end up seeing the fact that if I'm looking down at one point, I want to find, say, the inverse of this, the square root of that number. Well, I have two options. I have a positive and a negative square root, this blue line being the point that I'm interested in. So the fact that I have these two square roots means I need to make a choice typically, and a discontinuity in my choice where I move from one sheet to the other is where the branch cut will be. So the square root of z definitely has a branch cut somewhere in it. And of course, I can also see this from a logarithm standpoint. So you can see this graphically. But also by logarithms. And the reason for that is if I look at the inverse function, f inverse of w, which is w to the 1/2, let me write it out as e to the log of w to the 1/2. This is the complex log, not the natural log. This is e to the 1/2 log w. And 1/2 log w is 1/2 times the natural log, the real guy, of the magnitude, plus I times the argument of w, plus, and then there's some ambiguity, 2 pi I times n, where n is an integer, and it selects the branch. Bringing in that 1/2, you get sort of the obvious 1/2 here. 1/2 I times the argument w plus pi I times n. And since the pi I times n, along with the argument, this whole thing here, this indicates that I'm going to get two distinct roots. for each w. Why? Because 2 pi I would cover all of the possible imaginary parts, i.e. arguments, but I've only got a branch cut of interval of pi I, so I'll end up with 2 of them in the plane, and of course that's what's going on when we look at the graph over here. There's one over here and one down there. If I go ahead and continue to simplify a little bit, taking this formula, e to the 1/2 log w, that's e to the 1/2 all of this stuff. What I'll end up with is I'll end up with something that looks like e to the 1/2 ln w plus I arg w. Oops, I got an extra I here. Is this guy here, the first term, that first term is, was originally z. This was our z to begin with. So this is z times ei pi n. And this guy here is a 180-degree rotation. So if I take z squared to the 1/2 is z, or it's a multi-valued function, z to the I, pi times n, times 1, for instance. So this is the original value, and this is a extra copy. Graphically, this is the real part of z. This is the imaginary part of z. If I start out with a point z here that has r and theta, if I map it over real part of w, imaginary part of w, we'll get a point where the theta's been doubled. To theta, this is z squared, this is r squared. And there are 2 possible preimages, one of them being the original one and one new one. That new one being over here as well. And so this is the second square root that shows up. And so you can see that several different ways. You can see that algebraically, you can see that graphically here, and you can see it graphically from this surface. This surface is called a Riemann surface. So you can see that this z squared function has got a rather complicated structure. It has the multiple values except at the origin. The origin, looking at the Riemann surface, is a special point, a ramification point of which there's only one image. So in conclusion, z squared is kind of an involved function. What about z to the n for some n integer? Well, it wraps around n times. And that origin gets more and more twisted around. You get more sheets and more preimages. But algebraically, that's what you would expect, and graphically, now you know that's what you would expect as well.